my talk consists on comprehensive trap characterization and TCAD physics-based simulation studies for analyzing trapping mechanism in GaN-EMT, and also reduced NT also we will see later. So the potential application of the GaN-EMT are numerous, as you know, for power amplifier, for base station, power amplifier, for multi-tone power amplifier in space applications. So all those applications involve complex modulator signal, pulse phase, and also highly complex signal of OFDM that presented by Jacques Sombrun this morning. So here the AlGaN GaN-EMT ground on foreign substrate results in imperfect crystal with dislocation or defects. So these defects cause the formation of deep level state within the GaN also on the barrier. So deep level state act as traps for charge carrier in the band gap of the material. So surface trap could be formed due to defects or impurity formed at the surface during crystal growth or in device fabrication process. In the right side, I put also the possible physical location of traps in the device, and the main consequences of traps are gate lag, drain lag, and drain current collapse, DC RF dispersion. And trapping effects also contributes to dynamic error, which affect the power switching applications. So the thermal effect and trapping effect are difficult to separate, since the time constant are almost the same order of magnitude. So I will talk about trapping effect. My colleagues, Raphael Sommet, talk about the thermal effects. Okay. So concerning trap investigation, I will talk about pulse IV characterization, gate lag, drain lag, but we don't have any no information on the dynamic of the traps. That's why there is a lot of possibilities we can make by low frequency S parameter measurement, or also DCT current measurement. So then after I will talk about how we can identify physical location of traps. So we will use TCAD centralized physical simulation, and we will compare with measurement data. And finally, I will talk also about the trapping induced dynamic reduction in 2-deck density of GaN-EMT by using DCT current measurements. So what is a trap? Trap may be a discrete energy state located inside the band gap of a semiconductor, so capable of capturing and emitting an electron or a hole. So according the energy, we can classify two forms. So electron traps, that means energy level is below the conduction band, or all traps, that means energy level above the valence band. So trapping and detrapping mechanism can be analyzed with Shockley-Rideal mechanism statistics. So based on the charge state, the acceptor trap is negatively charged if it is occupied by an electron, or otherwise will be neutral. So the unoccupied donor state is positively charged and will be neutral if it's captured electron. So the trap signatures are activation energy and capture cross section. We will see how we can characterize activation energy and capture cross section. So the first thing, in order to look to investigate gate lag and drain lag effect, so we performed these measurements by using AMCAD built pulse IV system. I will show here the prof. I don't know if you'll see or not. Okay, the profile, the pulse profile. So we have taken 500 nanosecond for drain and period of 500 microsecond. So the pulse width, we can go more than 500 second also. There is not a limitation about this pulse profile. So as you can see, gate lag effect, we don't have any or very less reduction current. So we have do that, we have a bias point 0, and we pulse after the VGS and VDS. So we have in order to characterize gate lag effect, we have put bias point of -5 and VDSQ equal to 0. And I compare these two curves, and as you can see, there is very less current. That means very less surface traps. So due to probably the good passivation. But the deep off state quiescent bias point, that means for VDSQ 30 volt and VGSQ -5 and 10 volt and also -5 also for VGSQ, promotes strong electron trapping under gate and gate drain access region due to reverse bias gate drain voltage. So it's the current is dramatically reduced due to the trapping effect. You can see also the King effect, but the King effect disappears when VDS is pulsed from 20 volt to 0 volt because there is a detrapping of the electron. So as I said to you, we cannot, we can see there is traps by making this kind of measurement, but no dynamic information of trap we can obtain about with this kind of measurement. So we need to make other kind of measurements. So we made here low frequency S parameter measurement. I with Agilent VNA. So I present here imaginary part of Y22 versus frequency for different temperature. As you can see, the peak position shift is found to shift to the higher frequency when the with increasing temperature due to the increasing in the emission rate, and it is related to the emission time constant. So we will see with this we can characterize activation energy and capture cross section. So on the right side, I show also the imaginary part Y22 versus frequency for different value of VDSQ and also EDSQ varying from 50 milliamps per millimeter up to 150 milliamps per millimeter. So the frequency also, the peak position also shift when the bias point increase. So temperature dependent Y22 characteristics show the carrier emission rate increase with temperature. That is frequency dispersion Y22 properties signal follows the Arrhenius plot. So by taking the peak position by Y22, we can calculate emission time constant, and by taking into account the Arrhenius relation and by plotting the Arrhenius plot, we can obtain activation energy by looking the slope of Arrhenius and capture cross section from intercept of Arrhenius. So in this case for us, we have obtained around 0.42 electron volt and capture section around 503 e power minus 16 centimeter square. So for different value of VDSQ, 10 volt and different value of IDSQ also. As we can observe here, we don't observe any Pull-Frankel effect in this kind of transistor, which is a UMS device, is a GH15, that means 115 nanometer gate length and 8 cross 50 micrometer. So in order to understand or to see the localization of the traps, we use 2D TCAD simulation. So 2D cross section of the amps is taken for the simulation. So first thing you have to do, the physics model and material parameters are defined as device simulation. Then the first step, you have to make the calibration setup. That means you have to analyze, adjust the parameters of TCAD model and essential parameters in order to compare IV simulation result with measured data. And then once you have done that, we can make low frequency S parameter simulation. So for this, we have put the polarization charge at each material interface based on the work of aperture. So a fixed charge is of 1.4 e power 13 per centimeter square is put on the either side of GaN cap and AlGaN barrier, and to emulate the polarization produced in AlGaN-GaN structure. Then after we put also a fixed charge also of -2 e power 12 per centimeter square passivation silicon nitride and GaN cap. And finally, we put also surface donor between silicon nitride and GaN cap also with electron energy level of 0.3 electron volt below the conduction band, and with the density of 2 e power 13 in order to guarantee the generation of a two-dimensional electron gas in channel. And also we have put uniform effort doping in the buffer of 3 e power 16 per centimeter cube. As you can see, first thing is to make the calibration phase. So we have to adjust the essential parameter. In our case, we have adjusted the gate metal work function and also the iron concentration and electron effect of electron mobility. That is the first thing you have to do first, and also surface donors density in order to obtain as close as possible, because it's not to exactly to match is difficult, but as close as possible the simulation, IV simulation result with measured data. So we have done this first for 25 degrees Celsius, and then we have to do also for the calibration at different temperatures. So we have made this. I don't make this kind of slide for different temperature, but we have verified the calibration at different temperature. As you can see, after for the characterization of the simulation of traps, we use only a single set of physical parameters throughout the simulation. So here is the buffer trap parameters used are summarized in this table for the simulation. So we have introduced acceptor traps in the buffer. So effort doping introduced acceptor-like electron traps in the GaN buffer layer. And also we put surface donor traps in order to generate two-dimensional electron gas. So as you can see here in the simulation, here I present imaginary part Y22 versus frequency for 3 temperature for VDSQ 10 volt and EDSQ 50 milliamps per millimeter. So you can see also the peak position is found to shift also to the higher frequency with increasing the temperatures. Okay, so with this we can plot after Arrhenius plot, and then we can deduce also activation energy and capture cross section. So one of the good thing here, I present also the simulation of Y21. So with the Y21 we can see buffer trap and surface traps. So we have 2 peaks. One peak's position is positive, another one is negative. So as you can see, surface traps is a positive peak. So with this, also the peak position shift into the higher frequency also when the temperature increase. So by plotting, we can observe buffer trap and surface traps. So surface traps is 0.3 electron volt that we have already put on the simulation with the capture section, and also buffer traps. So with Y21, we can see two traps, buffer traps and surface traps. But with Y22, we can only see the buffer traps. That's one of the things I think for the modeling also it will be important to have this kind of measurement, but this kind of measurement is very difficult to obtain. So you have to make the good calibration of the VNA. So then we will see here the comparison between simulation results and measured data tracks closely. It's not possible to have a good agreement, but it's sufficient to see that the location of surface traps and buffer traps. So we obtain here the 0.2 electron volt of energy level for surface traps with a capture section of 1.5 e power minus 18 centimeter square, and buffer traps also around 0.4 electron volt with the capture section 2.3 e power minus 16 centimeter square. So with this kind of thing, we can locate the trap, identify the trap using the simulation. So that I tell you before, the shallow trap not detected from the Y22 parameters, but this will be a new method to identify surface traps and buffer traps using the imaginary part of Y21. So we make also some variation of the buffer trap parameters. So I present here the imaginary part Y22 versus frequency. When you increase activation energy, as you see, the peak position decrease, so it's a shift on the lower frequency. Contrary, when you increase the capture cross section, the peak position of Y22 increase. So variation of activation energy concerning the current. So the current decrease when the activation energy increase. And for the one of the good thing also, so for when you change the capture section or increase the capture section, the current doesn't show any variation. We make also the variation of the buffer trap parameters. So as you can see, on the left side, imaginary part Y22 versus frequency for different temperature. So the amplitude increase, but in the simulation depends on the density of buffer trap. So as you can see on the simulation, the amplitude of the peak position can decrease or increase. It depends on the density of buffer traps. So the current also decrease when the buffer trap increase. So now, so with this kind of measurement, we have seen that we can identify or calculate activation energy and capture cross section, but it's not possible to have density of buffer trap. So there is one idea for how you can determine trapping induced dynamic reduction. So as you know, is a well-known drain current in saturation region here. So we take the 2-DAG density by charge model NS. We have also threshold voltage. We combine all these equations in order to have simplified drain current expression as it is shown in the last line. So the phi b is the Schottky barrier height. So delta EC is the conduction band offset, and the important thing is delta D is the effective depth of 2-DAG channel for the hetero interface. So for this method, we use DCT current measurement. That means single pulse, only single pulse, because VDS is constant. We have taken 5 volt for VDS, and VGS is initially pulsed from one state off state to prompt charge trapping in the empty. So we use filling pulse of 1 second, and VGS fill voltage is -6 volts. And after, for the emission time emission is about 100 seconds we use. So VGS is is written to a semi-on bias point, and the emission transient current is measured with respect to time. So surface trapping, as I have shown before with the gate lag, is considerably mitigated by nitride passivation and feed plate configuration. And most of the electrons trapped in the barrier layer are transported to the 2DAG and are subsequently transferred to the buffer region due to the field assisted emission. So eventually the trapping induced reduction in 2DAG density restricts the maximum achievable IDS, that means reduced by delta IDS. Upon the empty is rapidly returned to its initial operational state. So we have tried to make an analytical expression. So I use the same thing, the pulse, single pulse measurement. So as you look, so the current IDS at T1 is reduced of the amount of NT due to the trapping electron in the buffer. And after the recovery, transient recovery, the steady state current is reached at T equal to infinity due to the detrapping mechanism phenomena. So by combining these two expressions, IDS at T1 and IDS at T infinity, we obtained the final expression IDS 0 over delta IDS, which is which gives a straight line versus VGS. So by taking this final expression, we can calculate NT from the slope of the expression IDS 0 over delta IDS. So we make this kind of thing for different structure. The first one is FDOPT algan-GaN empty. So what we have done here, I already present that activation energy of FDOPT algan-GaN is about 0.5 electron volt and 3 e power minus 16 centimeter square. Even with low frequency measurement or IDLT measurement, we have almost the same, but not exactly the same value, but almost the same. So we have already identified this. For estimate the value of NT, what we have done, we have the filling is always 1 second, and VGS value of VGS filling and drain filling is -6 and 5 volts, and we vary after the value of VG in order to modify the current also, and we have plot IDS 0 over delta IDS versus the VGM, variation of VGM. So as you can see, this is the measurement. So as you can see, really we have a straight line. So with this we can have the slope. With this slope we can determine also the NT, estimate the NT. So for this case FDOPT algan-GaN, we have estimate 3.4 e power 11 per centimeter square. We have already seen that this kind of traps are in the GaN buffer. So we have done also for CDOPT, a barrier with the indium aluminum nitride GaN. So on the left side I present the derivative of DCT in order to calculate the activation energy and capture cross section. For this kind of thing, CDOPT buffer, we have 0.14 electron volt with a capture section of 4 e power minus 18. And then we make the same thing by fixing the filling pulse always for 1 second with -5 volt and VD filling pulse is VD filling voltage is 5 volts, and we vary after the value of VG. So as you can see also, even for CDOPT, barrier difference, we obtain also a straight line. So we can with this kind of curve, we can have the slope. With the slope, we can estimate the NT. So for this case, for CDOPT, we have 9 e power 12 per centimeter square. And then we have made also for C-duct aluminum nitride barrier. So first you have to make the ideal TS measurement in order to have the activation energy and capture cross section. For this case, we have obtained activation energy of 0.33 and capture section is too small, is about 2 e power minus 20. That means for the C-duct, contrary for F-duct, the time constant is very low. As you can see, it depends on even 1 second or 10 seconds is very, very low for this kind of device structure. Because for F-duct is about 1 millisecond or 10 millisecond, but here you can reach more than 10 seconds. And then after we make the same thing, tape filling pulse is 1 second and minus 5 volt and VDS 5 volt, so that with this manner we can compare all the structure. So once again we obtain a straight line. With this straight line we can calculate the slope and then we can compute NT, and for this case we have 1.2 e power 13 per centimeters square in ALN GaN amped with C-duct buffer. So the conclusion of my talk here, so you have exact trap signature in ALGaN GaN with F-duct. So device gain length is 150 nanometer for 8 cross 50 micrometer. We have identified the location of traps using TCAD simulation. And as Y22 parameters, we don't have, I don't show you low frequency drain noise, but Y22 parameters and even DCT mostly sensitive to the buffer traps and even low frequency drain noise also. So new method to extract the signature of surface traps by using imaginary part of Y2N. So as I shown to you, Y2N parameters able to discriminate traps in both buffer and surface region. So as we have defined a simplified analytical expression to estimate the dynamic decrease in 2-deck density due to the buffer trapping effect. And we have validated this expression with F-duct and C-duct and also for different barrier. And we have obtained the value of activation energy, capture section, and also now the method to estimate the value of NT. So our derivation represents a good mean estimation to quantify current collapse in the amped, and it is an important first step before further improvements in the model for calculating the buffer trap concentration. So I want to thank UMS Foundry for supplying the device wafers. Thanks also to Mohamed Bouslama and Emmanuel Dupuy, and also for the agency and the International Research Project and also Campax. And thanks also to the PhD students of Higgs team for providing all the measurement characteristics. So thank you for your attention.
Interesting talk on the use of low frequency S parameter measurements to find out the trap characteristics. The paper is open for questions.
In aluminum indium nitride GaN HEMS, you extracted the activation energies for the carbon doped GaN buffer. So why is the difference that activation energies with carbon dope, that is 0.32 electron volt in one device you got 0.14 electron volt, whereas the carbon doped GaN buffers are giving carbon induced traps activation with 0.9 electron volt, which is literature reported in literature.
Sure, that's a good question, but I think for contrary for F-duct, for C-duct, it depends how you growth the carbon. That's the important thing. So that's why we can have the difference value of activation energy. That's the reliability of C-duct. That's a great problem because you can obtain 0.3 and 0.4. It depends on the growth of the carbon duct in the buffer. That's what I have seen, you know. For different structure coming from UMS or IMN is a little bit different.
One more question. I understand that from low frequency Y22 parameters you extracted this trap activation, which is related to buffer traps, and from Y21 you you got this buffer and surface layer trap. Now, how did you rule out the effect of the buffer traps or at the interface of the algae and GAN interface under the gate?
Your question is how I can identify if it's surface traps or buffer traps, no? So that we have done by TCAD simulation, that we have put also traps also in algal barrier in everywhere. So we have seen only when you put surface traps, silicon nitride and GAN cap, and buffer traps, you obtain the Y2N simulation. That's all. Because we have put everywhere first in order to test how we can obtain Y2N, even Y22. So that's why I say that we have two traps on the buffer one, on the surface traps, silicon nitride and GAN cap, and buffer traps on the.
But actually, if we do measurements,
yes,
low frequency Y2N measurements, and then we don't know where are the traps. Then the barrier traps can be one of the reason. Then how can you explain that?
That's possible, but that I tell you because in the simulation we put in algal barrier that we don't obtain anything.
So there is no effect of the
yeah, sure. That's we have obtained for these kind of things because we know now GH15, Eric Leclerc is here, so no gate-like effect, very low now. All the things is drain-like effect. That's now it's, I think surface is a very good thing now, is a very good passivation now. So I think it's stabilize devices, I think. But I don't see for CDOP because the Y2N measurement is very, very difficult because, you know, for the transistor, the S11 is near the 1. So it's very difficult to obtain Y2N, properly Y2N measurement. We have to make a lot of average in order to have this kind of measurements.
So any other questions? Yeah.
Considering surface traps in the GAN gap, and do you see any lateral change in the surface trap?
Along the surface?
Yeah, along the surface, if you
I think we will be near the edge of the gate. I think, you know, we haven't made the simulation properly, haven't seen anything, but we have to look about
any
this.
possibility that any effect of leakage part can be captured? Like the activation energies that you are calculating, any effect of leakage part that can be captured?
But probably we have to look by making the measurement, ideal TS measurement, making the measurement with the IGS. But the value of EGS is very, very low. So it's very difficult to have the measurements. So that's why I don't know exactly, but in the simulation, we don't observe like these kind of things. That's important, but I try to make the characterization with the gate source current measurement, but the current is very low. So it's impossible, for instance, to make this kind of measurement to know if it's coming by gate leakage or not.
In your IDVG measurements,
Yes.
the measured data had this slope of GM reduces.
Yes.
But experiments didn't have that. Experiments manifested.
I should. Here, no, you talk about the
So
IDS, VGS.
simulation data IDVG. So simulation are these colored solid layers.
Yeah, yeah.
So they don't have that GM drop off.
Yeah, sure, because it's difficult to obtain also
So
by.
any reason that what might be causing that GM drop off? Because as far as I knew, this is most probably caused by surface traps.
Yeah, because the Menegaso tells this kind of things. They're telling the surface traps it depends on GM and VT also. I think really I don't agree with this kind of, I don't know, but it's simple for me. So it's difficult to obtain this part. Why I tell you? Because when you make this, for all the things is for class AB power amplifier. So always I put near -2 or -1 volt. So I never go up to 0 volt now. So for me, is not a, that's why I cannot tell you, because 0 volt is, channel is open, so the Menegaso cells, sure, that depends, we can look surface traps and buffer traps by looking GM. I think I made a lot of things, but I never observed this.
That you have done simulation without reactor.
No.
So one question. The low frequency measurements, how low is low here? And second is the VNAs and all these tools are limited in terms of the bias that you can apply, the bias that you can couple. So was there any bias dependent aspect that you also studied? For example, some of these traps will not respond at low fields, but then you start seeing them basically responding to all these measurements when you go to high field conditions, but in the buffer. So under what field conditions or what bias conditions the measurements were done, and what's your thought on going to much higher fields?
Yeah, yes, I'll show you, but I cannot tell you because the VNA A5061B is specified for the bias tuning. I don't know inside how they make this. So you take into account all the things what you say, but it's the inside of the instrument. That's a great thing to, important thing to have the bias T. But I look only on the.
I know they sell this for impedance measurement.
Sure, but we can make also S parameter measurement and also admittance measurements.
But
so
the bias is always limited.
Yeah, but I think that's we have compared with the admittance measurement and also with S parameter measurement, we obtain the same thing, almost same thing with Y22. That's why I tell you with Y21 it will be difficult. We have to make seriously calibration properly. You have to make a lot of measurement. You have to be sure for that.
But the question I have, because somewhere I saw that voltages were limited to
Yes.
of 20 volts.
Yeah, but we make bias T for our proper bias T on the left side. Yeah.
Do you expect different behavior as you go to a few hundred volts?
Sorry.
Do you expect different behavior as you go to a few hundred volts?
We cannot do that. Yeah. Yeah, limitation of the bias T.
Okay.
Long live India and France friendship.